Okay, today's lab 7, we are going to show how to use the PID control, not just PI control, for to control the position of the motor. Okay, so if we open the position control.vi and run it with all the default settings, you can see over here it's position, not speed any longer, rotation speed. It's not rad per second, but the position, which means it's turning a specific angle of it. And you can see it's going back and forth only, but not rotating at a certain speed. Okay, so this is the position waveform, which is going back and forth, and so on. All right, so over here we have the PID controller, and this is the PID control, this is the motor, so it will give the the final output will come back to the PID controller for the negative feedback to a more accurate, precise control of the position of the motor. Okay. And this is the model of the PID controlling transfer function, not the transfer function, but the basically still transfer function in time domain. Okay, so and the PID control can be modeled as such, and the Kp can be calculated as this. This omega 0 will be given in the next few sections, and this tau and k are the parameters we measured in lab 6, the DC motor modeling. Okay, and this Kd is can be computed as this. If we this is the no load disturbance cases, and we usually do not need to consider about the Ki. But if we do have a load disturbance, okay, then we need to consider the Ki, and it can be calculated as these. Okay, so the Kp is slightly modified with this, and the Kd is with this, and the Ki is with this. Okay, so over here we are going to demonstrate the position control with the PID, or the first one without the disturbance, then only the PD control is sufficient. So over here we have set amplitude as 2, frequency 0.4, and offset 0, and let's select everything to 0. Okay, and this is the waveform. It is slightly different from the default setting if we change the Kd to 0. Okay, and this is the settings, and if we change the Kp increment by 2 or decreased by 0.25, then something will change, and it simply asks us to try the 0.5. Okay, so let's try 0.5. This is how it looks, and let's try 1. Okay, it will be changed. Oops. And if we make it 2, so it will be overdamped. All right, and if we change it to 4, there will be more oscillation to the signal, to the positions. Okay, let's go back to 2. And then it asks us to examine the measurement, actual measurements, and the reference point with the blue ones, and explain why this happened, and compute the steady state error, which we can. It's basically 0, but if you want more accurate measurements, you can stop it and zoom in the y-axis to do the measurement. Okay. And if we increase the derivative gain Kd by 0.1, okay, it will slightly change a little bit. So you'll see there's less oscillation after the overshooting. And if we continuously changing it, and the overshooting is getting smaller and smaller until it's going underdamped. Okay. No, overdamped. Okay, and so on. And what you need to do is to explain why changing this KD will change the overdamped or underdamped, the damping ratio of the waveform. Okay. Alright, so this is the basic modeling, and over here we have some basic parameters. So it's zeta equals to 0.6, omega 0, 25 rad per second, P0 equals to 0, and these values you can replace them into the values over here, okay, and do the computations for each KP, KD, and KI, okay, and then you set up the proper number for KP, KI, and KD into this, and you will observe the frequency, the waveform outputs, okay, and assuming I already have the number. Okay, I just a little bit calculations on that. Ki is still 0, and this is 0.77. You should get a similar number like I do. Okay. And over here, you should be able to see the steady state error, the overshooting percentage, and the rising the peak time, and so on. Let me pause it and zooming the value over here. So this y-axis, let's set up to 2.5, and let's set this to since I only need the peak time, which is starting from here to here, so let me just set this 1.5 first. So you can observe the steady state error, it's almost 0, and you can observe the rising time, the peak time, and also the overshooting percentage. Okay, and then what effect does changing the specific zeta means, and how it will be changed, changing the position response, and the control gains, and the peak time, overshooting, and so on. So you need to do a little bit calculations, and according to what I have over here for KP, KI, and KD, because zeta will affect these parameters and therefore affects the waveform over here. Let me get it back. Positive 5, negative 5. Okay, so I'll say negative 3. And this is making it 3 or 4. So we will have enough place for the overshooting. And if I simply just run it, let's make it 2, and it will be something like this, a lot of overshooting, and so on. And let me keep the KP constant, KI as constant, and just simply change the KD 0.2, okay, 0.4, 0.6. They were getting somehow, and let me get it back. 0.01. Oops, 0.1. Oops, that's too much. Now it's getting back to what we have previously, but there's a steady state error over here. And let me change the KP to 1. Previously it was 2. And if I change the KI to 0.05, okay. And 2, you'll see the difference between each other. Okay, so basically you have enough data of what we have over here and to compare the difference between changing Kp, Ki, and Kd, which actually means changing the zeta or changing the omega, how they will affect each other and therefore affect the waveform. Okay, so this is for the no load disturbance case, because I set the disturbance over here as off. But if I set the disturbance over here to be, say, let's as off over here, so this is the original waveform, okay? And if I change it to on, which goes to the next section, if I change the amplitude to 0 and turn this on and set it to 2, 0, and 0.02, oops, and run it, you'll see there's a disturbance or steady state offset between each other, and this will not be cancelled. If I simply set this as 2, oops, there will still be a steady state difference between each other, okay? But if I change this into 2 as well, then you'll see the steady state offset or error is getting smaller and smaller until it's almost 0. Okay. The only effect, the change we have done is changing this Ki, and you need to explain why this disturbance can be eliminated by changing this Ki. Okay. Alright, so that's basically what we have for the position control lab, and I need you to go through these process and these details and see if you can understand the entire process and explain the phenomenon we observe over here. Okay. You don't have to go through all the details over here, but in case you want to deal with it, feel free to do that.